stand up, all of you. Come over here. Not just one at a time. I need all of you. Don't just clap. Come over here. Yes, don't run to the exit. Run over here. Yes. You have the power. Nice to meet you too. Yes! For math and why they might not like math. So I think the biggest thing I want to talk about today is peer pressure. Now, peer pressure is when, you might not know if you're being affected by peer pressure because you just want to fit in. It's when everybody else is doing something and they scrutinize you, not scrutinize, but they stigmatize you and criticize you for not doing it yourself. And even though you're opposed to it, you feel that to actually fit in with society, to be like everybody else, you should resist it yourself, or you should do it yourself. And in this case, it is hating math. Many people are frightened by just the name of math. So I think it's just some peer pressure or just some myth that math is something that can only be done by geniuses on Einstein's level. I think that math can be done by everybody, and it's as accessible as any sport or any game or any other subject in general. So today I want to talk about calculus and infinite series. And you might be thinking, whoa there. Suborno, we're in 8th or 9th or 10th grade. Why are you doing this? Isn't this a little bit hard to fit in just a small lecture? Well, I'm going to try and start from the very beginning so that everybody can understand step by step by step. So let's start from the very basics. Functions. All right, does everybody know what a function is? Okay, so does anyone not know what a function is? What did I just hear? Okay, please raise your hand if you know what a function is. All right, that's good. That means that we have something new to teach. So let's say that we have every single integer. 0, 1, 2, and I'm ignoring the negatives here. 0, 1, 2, 3, 4, 5, 6, and so on. Now, let's say that I add 2 to every number over here, okay? So what happens if I add 2 to this? What do you get? Louder. What is this? Louder. What is this? Louder. What is this? What is this? What is this? And what is this? Okay. Okay, so now we have what we call a function. So what is the function in this case? We're adding 2. This in itself is just a function. But how do we express it? Well, let's clear this first. So essentially, when you're adding one of those like math graphics effects, you might see some of these scary things. These are just functions. So what is this? This is an input. This is what we put in. So, for example, what we put in now was 0, 1, 2, 3, 4, 5, 6, and so on. And then we added 2 for each of them. And then, what were our results from top to bottom? What is this? It should be a little bit louder next time. What is this? This? And I think we can do this pattern again. So, this is the output. This is the x, and this is the y. So now, what relation can we make here? Well, essentially, what we're doing here is the output is just the input, and then we add 2. Do you see why that is? Is that a yes or a no? You can't just nod your head. Louder. I don't know why I heard a no, but okay. So this is the concept of a function. So now let's try and make sense of this scary thing. Y equals 3x squared plus 7. So in this case, we already know the x. The x is just all of the integers. Of course, there are some others up this way, but here are the integers. And then, what is this anyway? Well, this is 3 times x squared. What does that mean? Well, it's just the input times itself. And then we're adding 7. All right. So, first of all, what is 3 times 0 plus 7? Louder. 21. Okay. And then, what is 3 times 1 plus 7? 8? Wait, what? Oh, 10. Okay, good. What is 3 times 2 plus 7? 19. What? I'm scared, confused, and repulsed. Okay, now, I'm just going to plug in the squares from now on. So what's 3 times 9 plus 7? 34. Oh, yeah, that's right. Okay, so now let's fill in the rest. We have 3 times 16 plus 7. This is going to be 48 plus 7, also known as 55. And then this keeps going on and on and on. So now, this is a function. So you might be asking, all right, that's a function. Good. So then, why do I see functions depicted as these weird little curves? So for example, 3x squared plus 7 might look a little bit like this. What does this mean? So let's start from the very basics once again. So you remember that y equals x plus 2 function we had on hand before, right? Okay. So now, if x is 0, what is y? If x is 1, what is y? If x is 2, what is y? Good. You're seeing the pattern now. So this is the x-axis. What does that mean? Scary number. A scary term, right? Well, what are we going to do? We're going to treat this like a number line. On this number line, this is 0. On this number line, this is 1, 2, 3, etc. This is like a number line, so that this is x equals 0. This is x equals 1. This is x equals 2. And in the same way, we have the y-axis is like a number line, rotated 90 degrees, so that we can actually see it depicted from a different dimension. So if x is 0, y is 2. Where is that on the number line? Well, we can approximate it to be right over here. To be more precise, I'm going to draw the little marks that you see on a number line. This is y equals 2. Then this is y equals 3. Then this is y equals 4. Okay. So now, what are we going to do? Well, you would agree that this entire line is x equals 0, right? Okay. What? That was a yes. Okay. So then, you would agree that this line right over here is y equals 2, right? Okay. So then, I want someone to come up here and tell me the intersection of this line x equals 0 and this line y equals 2. Oh yeah, someone's running. Oh, he's running outside. Okay. I want someone to run not outside, but on the stage. Anyone? Anyone? Oh, okay. Okay. That was a... What are they saying in the background? Are you guys actually focusing? Wait, what? What advanced technology is this? This is still white! How do I change the color? Oh, whatever. Okay. So now we're going to draw the lines x equals 1 and y equals 3. Where do they meet? Right over here. X equals 2 and y equals 4. Where do they meet? Right over here. So you see what happens when we connect the dots. This, and then this, and so on and so forth. All right, you say, this one is a straight line. But what happens if I calculate it for something like y equals x squared? If I have this, if x is 0, what is y? Louder. X equals 1. Y equals? X equals 2. Y equals? X equals 3. Y equals? Yes! You weren't supposed to answer that. All right. So, let's draw it on the board. All right. So, here's line number 1. We have 0. We have 1. We have 2. We have 3. We have 4. We have 5. We have 6. We have 7. We have 8. And we have 9. And now we're going to draw that on the y-axis. We have 3. We have 4. We have 5, 6, 7, 8, and 9. All right. So when x is 0, y is? Okay, so where do we put it? Right here? All right, x equals 1, y equals? So where do we put it? Right here? X equals 2, y equals 4. So where do we put it? Here? All right, x equals 3, y equals 9. So where do we put it? Here? Uh-oh, that's y equals 8. Are you telling me that 3 times 3 is 8? So maybe pay closer attention. Do we put it here? Do we put it here? Yeah. Okay. But now let's look at the graph. We connect the dots. 1, 2, and 3. The dots are connected. But does that mean that this graph just looks like this, a bunch of straight lines? No. And why is that? Well, that's because x squared, you don't just square integers, you can also square any number, any decimal. So that means that in between here, we can see unlimited amounts of squares. So if you take the value of 0.5, if you take the value of 1.5, if you take the value at 2.5, which is about here, and so on and so forth, your approximation will be slightly better. So in this case, it looks a little bit like this. So your approximation will be a bit better, but still not perfect. You have to keep going and going and going and going until you finally reach the correct curve, which looks something like, do any of you know how to change the color? Then come up here and show me how to do it. Now, we draw the line, the curve, which contains everything. And this is the true curve, y equals x squared. Okay. So now, you might be asking, well, wait a minute. You have a good approximation when we go by steps of 1, so like 1, 2, 3, 4, 5. So you have a good approximation when we go by a step of 1. You have a better approximation, but still not perfect, when we do a step of 0.5. So just like so. You probably have a better approximation when you do 0.25. So like this. But that wouldn't make it perfect, right? Because it can be squared over every single real number. So would that mean the step has to be 0? So what happens when the step is 0? Wouldn't we have to consider every single number? 0, 0.0, wait a second. If the step is 0, wouldn't this just be 0? How does any of this make sense? How do we actually find the true curve y equals x squared, if it even exists? Well, wait, did I just erase the toolbar sign? I've got the power. Okay, so now, let's see what I mean by that. Oh, now you all are leaving. You've been bored by the math, huh? Okay, so let's start with one of these curves, actually. So what we're going to talk about now are what we call limits. What is a limit? Well, let's say that we have, I don't know. Yeah, okay. So let's say that we just have the straight line function. So for this straight line, we have that for any point, the distance to the x-axis is equal to the distance to the y-axis. What would that make this? Louder? It's y equals x. How sad. Okay, so that's because this length, which is y, is equal to this length, which is x. You see that? Good. All right. So now, let's say that we want to approach a certain point. Let's say we're trying to approach the point where x is equal to 2.03. Sounds like a good number, right? Okay. Would you rather I use another number? Okay. I hear some people shouting yes, but I'm just not going to acknowledge them, which is the sad part. All right. So, if x equals 2.03, y equals? Louder. Yes. Not 2.06. All right. But let's say we're trying to find it at x equals 2.01. All right? So if x is 2.01, y equals? Okay. Now what about x equals 2.05? Y equals? All right. So what does this mean? Well, to make it a little bit clearer, I'm going to choose a function that's actually a little bit more rational. So let's choose this function, which is x minus 2 divided by x minus 2 times x plus 1. What does this graph look like? Well, let's think about it. Okay. Well, when we're dividing x minus 2 by x minus 2, what do we get? Okay, 1. Good. But what happens when we plug in x equals 2 to get 2 minus 2 over 2 minus 2? What is this? Louder. Yes! Now we have two competing teams, 0 and 1. And the even better thing is, neither of them are correct. 25? Okay, so this is 0 over 0. Are you telling me that's 0? And are you telling me that's 1? Louder. Yes. Now we've condensed us all into one team. We're all on the same page. This is undefined. All right. All right. But that doesn't mean we can't try to take the value at x equals 2, right? Let's see what this actually looks like. All right. So for x equals 1, what is this? What is this for x equals 1? No, the whole thing. This. No, like actually plug in this value. 2, finally, you've got it. Okay, this is 1, this is 2. All right, what happens if we plug in 1.5? What do we get? 2.5, that's right. No, like, what did that kid scream? I wasn't listening. Okay, and now, what happens if we take x equals 2.5? Louder! Yes! Okay. All right. And we know that at 2, it's undefined, right? So, shouldn't be here. But what happens when we take x equals 1.75? X equals 1.75. What is this? Louder. Good. This is 2.75. And then what happens if we take x equals 2.25? Louder. Good. This is 3.25. And you see what's going on here? We are getting closer and closer to whatever this value is as we get closer to the x value of 2. And it turns out that we're actually approaching, as you can probably guess, the value of 3. Can you see why that is? Louder? Why are some of you saying 3? Like, it's good that you're actually reading the whiteboard. I mean, I know that you're paying attention, but, like... And why is some kid screaming in the back? What is going on back there? Is anyone from there listening? Or are the kids just making random noises? And now someone is finally honest. I hear some kids say, random noises. Oh, God. Who am I teaching? All right. So now, let's actually talk about some functions that are a little more interesting with limits. Oh, I'm so done with this. All right. So, I'm going to review the sine function because I know I'm talking to a general audience right now. And it looks like that general audience has suddenly become a half general audience because people are leaving. But let's say that we have a circle right here, okay? Is this a circle? Why are you guys so rude? You have to tell me my circle's not. Oh, we have to go to the next session now? Okay, no, I'm just kidding. Okay, at least you learned what limits are. And I'm going to give you now I'm just going to give you, just give me one more minute, a formal definition that if you take the function f of a or f of x and you want to find its limit at a, so x equals a, so then the limit as x approaches a of f of x is equal to some number b if we can kind of shift in this direction and shift back in this other direction to produce whatever variant we want in B. So essentially, that means we can get arbitrarily close to the value B by getting closer and closer to the value A. So that's the definition of a limit. Unfortunately, it looks like we don't have any more time. Thank you, everybody, for watching.
What an enlightening talk. Let's give another round of applause.